single displacement, the situation will be there will be something by itself like Mario, something will be in a compound like Luigi and Peach, and then after the reaction, the compound now has the Mario, the thing that was by itself, and the thing that was in the compound, Luigi, is then by himself. So here it is with chemicals. You can see here that the Fe is lonely, and then it's in a compound, whereas the copper, right? So then the copper here is in a compound, and then it goes to being lonely. All right, and there's an image of it. So how are we going to predict these things? If you look at this chart just in general, you'll see here at the bottom are the things we make jewelry out of: silver, gold, and platinum. The silver, gold, and platinum are used for jewelry because they do not lose electrons. They tend to stay together and they're very stable in that regard. The things up here, lithium, rubidium, potassium, barium, those are the things that if you throw them in water, they start reacting, as we saw in class, that they'll start catching on fire. So these things will prefer to lose electrons and become ions, whereas these things tend to keep their electrons. You can wash your hands with a gold jewelry on it or with silver or platinum on your hands. It won't dissolve, it won't go away, and that's why we use those things for jewelry. Lithium is what we use in batteries because it's up here and it likes to very quickly lose its electrons. So the elements on the top prefer to become ions. The elements at the bottom prefer to stay uncharged neutral metals. And that has to do with their with their electronegativity, as you can see here. The palladiums, the silvers, the golds, the platinums, very high electronegativities, close to what carbon is, whereas the other ones, things over here, lithium, potassium, sodium, they're very low, so they'll lose their electrons. All right, so step process for doing single replacement. You need to first, when you switch things around, adjust the subscripts to create whatever product it is you're doing. So in this case, tin was with sulfate and sodium was by itself. I had to switch the tin and the sodium. So tin's by itself, that's easy. But sodium now is sulfate. Because sulfate is a -2, it needed two sodiums to make that neutralize to zero. So two sodiums are doing the job of one tin because tin had a +2 charge and those two sodiums have a +1 charge. Sulfate, you may recall, is on here. So sulfate's right there. It has a -2 charge. All right. So then the second step we're going to do is then balance it. So now that we have two sodiums on this side of things, we need a two over here to account for that. Our tins has one each and our four oxygens. That's fine. One sulfur. Everything else is fine. All right, so let's do some of these. Uh, if we're in a situation like this and the metal is lower than the metal it's trying to replace, they won't replace. So aluminum is here. All right, so higher up on the activity series, likes to be with a couple, likes to lose its electrons. Iron, on the other hand, is much lower. Okay, so iron would prefer to be alone when compared to aluminum because aluminum's higher up. It would prefer to be with something. So these things are going to switch places. So the first step is to then put the aluminum with the hydroxide and then put the iron by itself. Now, since iron's by itself, we don't have to do anything with that. With the aluminum, though, we have to make sure that the product that we create is actually what happens when aluminum's with hydroxide. So aluminum has a +3 charge. How do we know that? We know that because no, nowhere near. Here it is. Aluminum has a +3 charge. All right. So aluminum has a +3 charge. Then um, hydroxide, we know, has a -1 charge, and that's because it's on here. Here it is. Hydroxide has a -1 charge. So if aluminum is going to create a product with hydroxide, it's going to need three hydroxides to neutralize its charge to zero. So we need three of these to neutralize that aluminum. Now we've done step one. We determined the products and adjusted subscripts. That subscript needed adjusted because aluminum doesn't have the exact same charge of iron, so when they switch out, there's a difference. Now we need to balance, and we balance without adjusting the subscripts. There's two OHs here, there's three here. So we're going to need a 3 in front of here. 3 times 2 is 6. And then a 2 in front of here. 2 times 3 is 6. That's going to give us two aluminums. There's only one aluminum here, so we'll need a 2 in front of there. This will give us three irons. There's only one iron here, so we need to put a 3 there. All right, so doing this next one, calcium with silver. Silver is down here. It would prefer to be alone versus calcium, which is way up here. This would prefer to be with something. So calcium in the presence of silver nitrate will want to switch places. So that means the calcium will want to be with the nitrate and the silver will want to be by itself. All right. So what we have to do is adjust the charges here for the calcium nitrate. Now calcium is in group 2. Hold on while we do this. Don't get too car sick. Here it is. Calcium +2. All right. So that's the calcium. That's not the same as the silver. So this is +2. The nitrate, if we go to our chart, the nitrate is a -1. So nitrate's -1 and calcium is +2. That would mean I need two nitrates to counterbalance, to, what's the word I keep using? Neutralize that charge. +2 -1 is a total of is a total of 0. So we need two nitrates. We can manipulate the subscripts in the sense that we need that whole polyatomic twice. We keep the NO3 together because it's a polyatomic. It was on that list, but we need that whole thing twice to neutralize the charge of calcium. Now we do the balancing, and the balancing for this one is we have two nitrates. They all came from here, so we need a 2 there. That in turn gives us two silvers, so we need a 2 there, but there's only one calcium, so the calciums are fine. So copper with potassium, this is one of those examples. In fact, I'll do it in a whole different color because copper is here and potassium is here. So potassium's really high up, wants to be with a partner. So potassium wants a partner and has it. And copper wants to be alone because it's way down low. This is why we have our copper pipes and copper wiring in our house. So this one wants to be alone and it is alone. So since it's already alone and it wants to be alone, and since that's already with a partner and it wants a partner, we say that no reaction occurs. All right, so then magnesium and zinc. Magnesium and zinc, let's take a look at those. Uh, we'll go with a lighter blue. Magnesium is up here and zinc is down here. So of those two, zinc wants to be alone, so they are going to switch places. And magnesium will get with the chlorine and zinc will be by itself. Now in this case, magnesium and zinc both have the same charge. So zinc has a +2 charge and magnesium has a +2 charge. And since they both have the same charge, you can literally interchange them. There's really no difference between the two. So since this is +2 and this is +2, each chlorine's -1, they pretty much require the exact same number of chlorines. So in this case, chlorine did keep its subscript, but that's just because magnesium and zinc had the exact same charge, and it wasn't that big a deal switching them around. So then coefficient wise, we don't need to change anything. There's one magnesium, there's two chlorines, and there's one zinc. All right. So this is what we did. Let's talk about metal with water. So in this area here, all of these metals will replace water. And if we want to see that real quick, so sodium is a really soft metal. It's kind of like clay. And as you see here, when he throws it in water, it catches on fire. Now that doesn't really look like water because it's so murky, but he then throws it over here so you can see it a little better catch on fire with water. So that's what we mean when we say metals catching on fire with water. All right, now, so for these cases, what's catching on fire is the H2, the hydrogen gas. That's the Hindenburg situation. So sodium and water. One way to look at water, I've told you, is sort of an HOH. Okay, so water is H2O, which means there's two hydrogens and an oxygen. So if you look at it as HOH, then the sodium is going to switch places with the H. And you're going to get NaOH plus H2. H2 gas is what's released. That's what happens when hydrogen's by itself. Okay, so this is still a single replacement. The hydrogen is going by itself. It goes as a diatomic because it's a gas and it's one of the diatomics, and then sodium takes its place. So again, we need to figure out what happens here. How do we balance this? And sodium has a charge of +1. Sodium is +1. And the hydroxide, as we discussed, is -1. If you need to know why that's true, hydroxide will have a -1 charge on this chart here. Hydroxide is -1. So if hydroxide's -1 and sodium's +1, you only need one of each. So that is already established. Hydrogen is hydrogen gas. Balancing this reaction, we're now not going to mess with the subscripts. Everything is set. We need at least two of these to provide enough hydrogens for all this because there's two here and one here. So now there's two oxygens. So we need a two here to account for the two oxygens. And that means there's two sodiums. So we need a two there. So for this next one, we're going to switch out the, let's turn it green, calcium with the hydrogen. So calcium will now be with hydroxide and H2. Okay. Calcium has a +2 charge. So in manipulating this, if hydroxide had the -1 charge, we would need two of these. So let's take a quick look at what I'm talking about there. I'm talking about calcium having a +2 charge, and I'm talking about hydroxide having a -1 charge. So if calcium and hydroxide are going to have that situation, then we'll need two of these to provide two -1s and neutralize that charge. Now we're going to balance, and as we balance, there's one calcium, there's one oxygen, but there's two oxygens here, so we need a two there. Now there's two oxygens and two oxygens. There's four hydrogens, two hydrogens there, and two there is four. So this last one, silver, silver is not in that box. So that's not going to happen. Calcium was in that box. Sodium was in that box, but silver is not. So this is going to be no reaction. And you should know this, right? If you're wearing a silver ring and you wash your hands, it doesn't dissolve. Okay. So with acids, I don't know what noise that was I just made, but when we're dealing with acids, now we're dealing with this whole box here. Everything in this box, all these metals, are going to react with acid. Same situation, it's an H and some anion. Instead of OH, it's going to be Cl or NO3 or H2SO4, whatever. Some anion's going to be there. But all of those metals will do it. Again, the jewelry metals don't, copper doesn't. That's why we use copper wiring and whatnot. So this last one, right? Gold is not going to react. There's going to be no reaction. But let's get into the ones that are reactions. So let's look first at zinc. switching place with HCl. So zinc's here. It's in that box. It's going to do a switcheroo. So zinc will be with the chlorine, and hydrogen will again become H2. Zinc, we already discussed, has a +2 charge. Each chlorine has a -1. So we need 2 to neutralize that charge. So we need 2 chlorines. I didn't really need the parentheses there, actually. All right, so it's 2 chlorines for every zinc. And then after we've established that product, now we establish the char, or now we can do the balancing. I have 2 chlorines here, so I need a 2 there. That gives me 2 H's. I got a 2 there. Everything else is good to go. Magnesium is also +2. Magnesium is up here somewhere. There it is. So that's a +2. It's going to do exactly what zinc did. It's going to get together with the Cl. It's going to make H2. Because this is +2 and each chlorine is -1, it needs 2 chlorines to neutralize its charge. And then when we're balancing that equation, we're going to have the same situation where we need 2 of those and nothing else. Calcium is also +2. I don't know why we chose these, but we did. Calcium, we'll do dark red, I guess. So calcium's up here. It's also +2, but now it's getting together with nitrate. And nitrate is on that right polyatomic chart. Nitrate is up here. It's got a -1 charge. So with nitrate, there we go. It's got a -1 charge. So with nitrate, we want to, oh, I made my stuff go away. I was about to say, where'd everything go? Okay. So calcium's +2. Nitrate is -1. Calcium and hydrogen are going to switch places, right? They're in this box of removing acids, for hydrogen from acids. That's why hydrogen's actually here. So it's going to make H2 and it's going to make calcium nitrate. Since nitrate's -1 and calcium's +2, we need 2 nitrates. We keep the subscript there because it's that polyatomic. And then we need the whole thing twice to neutralize the charge on calcium. And then if we're going to balance, it's going to be um, probably 2 of these, right? Because we need 2 nitrates and 2 hydrogens. There you go. And then this one, as we said, no reaction because gold is not in that red circle. All right. So if you've ever had this situation where you make an acidic food, something with tomatoes or vinegar, and you have your aluminum foil sort of sticking to it, that's because aluminum's up here. And aluminum will replace hydrogen from steam. So if you had a lot of steam and the coating on the aluminum foil came off, that's supposed to prevent that from happening. You could get the aluminum sticking. Also, if you use an acid like vinegar, that could happen as well.